Great. Is now the normal view, I guess?
Yep.
Okay. Yeah, thanks a lot for the introduction. So good afternoon, everyone. I'm Wei-Tse from the University of Colorado Boulder, and I will be the lecturer for today's session, which is about running enhanced sampling simulations in parallel on HPC systems. So before we get into the details of running parallel simulations on HPC systems, we need to first understand what HPC systems are. So HPC, or high performance computing systems, are powerful computing systems designed to perform complex and resource intensive tasks on a much faster rate than traditional computing systems. So one HPC system you have been using in the past 2 days is the workshop. In this workshop is the Bridges-2 cluster, where a cluster means a group of interconnected computers, or more formally, a group of interconnected nodes. So just like most of the other HPC systems, Bridges-2 has several login nodes and a large number of compute nodes. And as a user, you can access the login nodes either using your terminal or your web portal like on-demand that we've been using in this workshop. So the login node generally has lower computational power and is meant for managing your files and data or submitting your jobs to the queue for execution on the compute nodes. From the login nodes, you can access the shared data storage and the powerful compute nodes, which are for computationally expensive tasks, such as running a bunch of MD simulations in parallel. So these compute nodes are often divided into different groups, or what we call as partitions. For example, we have been using the RM partition in this workshop, where RM stands for regular memory. Other than that, we also have partitions with large memory or extreme memory or even GPU nodes. So to access the compute nodes, we can launch an interactive session by a command called interact, although different HPC systems might have different commands for this. And the Jupyter notebooks that we've been running in this workshop are actually launched by interactive sessions where this interact command was executed internally by on-demand. And the compute nodes can also be accessed by a Slurm job submission script, which is a shell script that specifies the resources you want to request and the command you want to execute on the compute nodes. So this is more suitable for running long simulations where an interactive environment is not needed. And for more details about available options in a job submission script, you can always look up the user guide of the HPC system that you are using. So the best thing about compute nodes is that they enable parallel computing, so you can run a large number of MD simulations simultaneously. Generally, parallelization can be performed across multiple cores in a single node using multiple threads, such as OpenMP threads. It can also be performed across multiple nodes with using multiple MPI processes by OpenMPI, which is launched by command lines tools such as MPI run or MPI exec. And when you have a lot of computational resources at hand, one important question to think about is the best way to make use of these resources when running your simulations in parallel, especially because more computational costs will be spent on the communications when more nodes are requested. So as an example, here is a plot showing how the performance of MD simulations scale with computational resources. And you can see that due to the cost of communications, the performance generally does not double when we run the simulations using twice as many resources. When more nodes or cores are used to run simulations, more resources will be spent on communications between them. And at the same point, at some point, you will see the performance becomes sublinear, which means that the simulation you are running are not cost effective anymore. So to get it familiarized with running simulations in parallel using HPC systems, here is the first exercise that we are going to do right now. So here I'm in the on-demand web page. So I'm going to launch a new Jupyter notebook. And for the first half of this today's section, let me see. Yeah, for the first half, we are going to request a 2-hour interactive session, and we are going to use 32 cores, so you can specify n tags per node equals to 32. And here is just a comment that I personally use to get me to the home directory where I have the GitHub repo. So I'll just launch the notebook. This will probably take a few minutes, and yeah, so make sure that your GitHub repository is up to date. If you have like uncommitted changes, you can use the command like git commit. Or if you don't have any changes that are not committed, then you can use git pull to get the updates from the remote repository. Yeah, so something like this, you go to your local repo and you use git status. If there are like red lines, that means that you have like uncommitted changes, then you should do git commit to push the changes to your local repository. If you don't have any uncommitted changes as I do, then you can just probably use git pull to make sure that everything is up to date like this. So I just pulled a new contents from the remote repository because somebody has just pushed something new. Okay, so now the Jupyter notebook is ready. We can just launch the Jupyter homepage. So the folder that we are going to focus on today is Wednesday folder. And there are like 5 subfolders corresponding to 5 exercises. And in the input folders, you can see that we have like folders for different systems that we're going to use today. And basically, there are just like a bunch of Grow files, MDB files, and TOP files that we are going to use. So let's just click on the first exercise. Okay, so I'm using exactly the same notebook as you have if you have up-to-date local repository, but I'm going to present this notebook using in the form of presentation slides. Okay, so this is our first exercise, which is about performing multiple independent MD simulations in parallel. So this is nothing fancy. This is not an advanced sampling method, but just to run a bunch of independent simulations in parallel on HPC systems such as Bridges 2. So the goal of this exercise is to get you familiarized with running multiple simulations in parallel using HPC systems. So first of all, the goal of this exercise is to run 4 independent standard NPT MD simulations of the NaCl system in parallel. So this NaCl system that we're going to use today is exactly the same as the one we used for metadynamics tutorial. So each of the 4 simulations will be performed for 500 picoseconds. And as we just did, we requested 32 cores for this interactive session. So here are just a bunch of comments that I use to get rid of output directory. So you can just execute the cell, and then we can go on to the next one. And to get started, because right now we are going to run 4 independent simulations in parallel. That means that we need 4 directories, 4 folders for each of these simulations. So there are several steps that we can use to set up this example. First of all, we are going to create 4 folders like sim1, sim2, sim3, and sim4. And for each folder, we are going to copy over the input files from the input directories that I showed you, including the Grow file, TOP file, and MDB file. And with these 3 files, you should be able to run like gromx grunt command to generate a TPR file, where which you can use to run MD-run gromx MD simulations. So these steps are basically done by this show commands. Here we have to module load the gromx and open MPI in every cell we want if we want to use gromx or MPI. And also as a reminder, today we need to use the IPy kernel as the kernel for the Jupyter notebook. So i-CoMSE CPU kernel probably will not work for this purpose. And we are just going to run the commands here. So this is fine. This is just like not copying some specific folder, but we don't need that folder in this exercise. So we can just check if there's any error, and if there's not, then we can go on to the next one. So after setting up the simulation inputs, like the TPR files, we can now run the MD-run simulation. So basically, it's pretty much the same as running a standard MD simulation, like just one single simulation. The only thing that is different is that now we are using this multi-dir option to specify the folders where we have the simulation inputs. So here I just specify all the input files here. And in this cell, you can see that, let me see. Yeah, you can see that I have some additional flags. So for example, like this md-run command is launched by MPI run, which will run the simulations using multiple MPI processes. So here, -mp is the option that we can use to specify the number of MPI processes. And because now we have 4 simulations, in this case, the value of -mp must be a multiple of 4. So now we are using 8 MPI processes as an example. And for each of the MPI process, we will be using 2 OpenMP threads. So -NTOMP basically specifies the number of OpenMP threads per MPI process. And generally, each OpenMP thread will use 1 CPU core. So we have 8 MPI processes and 2 CPU cores per each. So that means that we are using 16 CPU cores for this specific command. So we'll just execute this command, and it should take like probably just 1 minute or 2. And in the meanwhile, I'll check the chat to see if there's any question. Okay. Oh yeah, RM small partition gets the whole node. So I should probably use the RM shared. I just
yeah, that's true.
Yeah.
So if most people are using RM shared, that's fine. But
yeah.
But if
I probably clicked
might,
the wrong one.
Wei-Tse, you stay on. But if other people did RM small, you should probably quit this and do RM shared, or quit it after. Like if people run RM shared for, if people are in RM small for like 5 or 10 minutes, it doesn't matter. But if it's for 2 hours, then it starts draining the allocation fast.
Yeah, so just to clarify, each RM node on Bridges 2 has like 128 cores. If you are using RM small node partition, even if you are requesting like 32 cores, like the whole node of 128 cores will be allocated to you, and that will cost like your budget. So
yeah, we've lost a third of our allocation in a week.
Use RM shared. Yeah.
Okay. Okay, no, we're in the past we've done that when we accidentally forgot it. So
I see.
Yeah. Okay. So now the simulations has been done. So here are just some notes that I just went through. We used 8 MPI processes, and each MPI process used 2 open MP threads, so that we use like 16 CPU cores. So because we just requested like 32 cores, that means that the other 16 CPU cores were actually idle during the simulation. But we requested 32 cores just for the scaling test that we are going to run later. So yeah, it should. Yeah, so right now here is the CPU scaling test. So what is like the motivation of the CPU scaling test? Basically, we want to determine a more efficient or more cost-effective way to allocate the computational resources for running MD simulations. So it is very common to perform a scaling test. Scaling test typically involves timing several short simulations with varying values of -mp or -NTOMP, and then you can plot the performance as a function of the computational resources that you use to try to find the cutoff point, the king point that I showed you in the presentation, to like tell like how much computational resources should be used to run your simulations. So here in this exercise, we are going to try to run 4 simulations in parallel using 4 different values of NTOMP, including 1, 2, 4, and 8. And in this case, we are going to fix -mp at 4. So you can imagine in the case where we use NTO NP equals to 8 and NP equals to 4, we will be using 32 CPU. In this part, we are going to find the optimal number of open NP threads per MPI processes. So because the simulations is going to take a while, I'll just maybe I'll just do the normal folder. Okay, so basically to extract the performance from to get the performance of each MD simulation, we can parse the log file, and here is a little function that I wrote that could be useful for getting the number of nanoseconds per day from a log file of the MD simulations that you are going to run. Okay, so here is the bash commands that I use to run a bunch of simulations. So here I'm using a for loop, looping over different numbers of NTO NP values. Notably, like in each iteration, we are running 4 simulations in parallel using MPI. So that means that we actually will be running like 16 simulations in 4 batches. So this is gonna take like about 2 minutes and like 30 seconds or so. And meanwhile, I'll check the chat. Is there a way to let me see. Is there a way to automate the naming of the simulation directories, for example, by using the for loop? Yeah, so basically what I did at the beginning was in each iteration I used like mkdir so here is an example, like I'm using a $sign here for the variable I. So the value of I will replace this plus with 1, 2, 4, and 8. So you will get like different you can use it as a variable. So you can do that for the naming of your folder. So that's doable.
Well, that's sort of like shell scripting outside of MPI run.
Right.
You could do it with Python with system calls in Python as well. So
yeah. That is a good question. Why are we using MPI if we're running everything on one node? So this is just a very simple small system. So one node is sufficient. MPI certainly can allow you run simulations on multiple nodes. And one thing about MPI processes is that although MPI processes can be for like communications between nodes, it can also be used to run like communications within one node. So this is just like an illustrative example that we are using MPI processes, but normally we could also use that for like multiple nodes.
Yeah, but things like Plume, for example, when it's running multiple processes, I think it requires MPI. It requires MPI even though it's just on one node, right?
Yeah. Okay, now the simulation are done. So let's go on to the next cell. So here are just like it is just a description about what we've just done. We varied a different number, the number of NTO NP, and then there should be a kink point for most of the time, but as we will see later in this case, for like very small system, the behavior might not be always expected. So here are just a bunch of lines that I use to set up my the plotting settings that I prefer. So here we can just plot the figure, and you can see that actually the linear region is here, and like the performance went down like after using like 8 cores, and that is actually kind of like not common in a CPU scaling test, and this is probably because that we are using a very small system. Given a large system like the system you would typically use for your research project, a CPU scaling test will give you a figure that I showed you in the presentation, such that there is a linear region, and then after some kink point, then the performance will become sublinear. So The result we got here is not ideal, but hopefully that still makes the point that it is important to run CPU scaling tests whenever you are kicking off a new project and using like a new test systems or new simulation method. We could have like requested 128 cores to test a wider range of the number of cores, but considering the available computing resources, we are only doing 32 cores. But if you have like more resources, and you can just run very short simulations for your scaling tests when you are doing your research projects. So the takeaways of this notebook is that GROMACS simulations can be performed in parallel using the multi-dir option. And also it is important to run a scaling test for your system or simulation method if you are planning to spend a lot of computational resources on them. So that ends our first exercise. So I will go back to my presentation slides. Okay, is everyone seeing my slides in a normal mode?
Yes.
Yes.
Okay, nice. Thank you. So yeah, right now we just
Let's pause if there's any questions that people have.
Oh yeah, okay.
If you had a much bigger system, you'd have to do things like you'd almost certainly have things like multiple, 30 cores per system. And then if you're doing copies of those, then that'd be on top of that. So Bridges actually makes it much easier than a lot of systems because there's 128 cores on a node. So frequently you only have to use one node. Well, a lot of the questions about which MPI version. Oh gosh, that just gets to be a mess. The best thing to do, whatever supercomputing system you're on, if you have to compile something yourself, check with the maintainers of that cluster about what MPI version you can use, because the best one to use is so dependent on what the environment is that they have and what the interconnects are and everything. You should defer to them as much as possible on those.
Yeah, that's right. Okay, so I guess I'll continue with my presentation. If there is no further question. Okay. Yeah, so what I was showing you in the first exercise was just a bunch of standard MD simulations running simultaneously. So now I'm going to introduce you several advanced sampling methods that are particularly suitable for parallelization. And the first method that I'm introducing here is umbrella sampling. And just like metadynamics, umbrella sampling is another useful method that allows us to compute the free energy profile as a function of chosen collective variable. So as an example, let's consider the NaCO system that you have probably already very familiar with. This is the system that we used yesterday. And for the system, one of the good collective variables is the ion pair distance. So umbrella sampling is typically composed of two steps. And the first step is what we call as the pooling simulation, or someone would call it as the stir MD simulation. So in the pooling simulation, we need to select a part of the system and fix its position and pull the another part of the system away. So in this example, we can choose to fix the sodium ion and pull the chloride ion away. And during this pooling simulation, the system would get the chance to sample different values of the ion pair distance. And the purpose of the pooling simulation is to generate a bunch of configurations at different values of CV from its trajectory. And these configurations can be used as the initial configurations for the second step, which is the production runs. So in the animation, you can see that we have generated 47 configurations from the pooling simulation, and each of them has a different ion pair distance. So taking the system as an example, in the production runs, we then need to run one simulation for each of these 47 configurations with a harmonic restraint. So the purpose of this harmonic restraint is to pin each of these configurations at a specific CV value to force the system to sample the region around that CV value. As these configurations tend to drift back to the nearest metastable states, the force constant must be large enough to pin down all these configurations. However, if the force constant can it cannot be. However, the force constant also should not be too large at the same time. Otherwise, the spread of each CV distribution will be too narrow, and there will be no overlap between the neighboring distributions. But why do we need overlap between distributions? In this case, you can imagine that if we are launching a simulation from the associated states, then the system could sample like this range of the CV value. And if you want the system to jump to like the dissociated states immediately, then say that we are looking at this state, then we basically are requiring the system to sample another CV range values that is not having any overlap with our original CV range. This is why in standard MD simulation, to jump from one end state to the other is very difficult, and that's why we need an advanced sampling method. And basically, the idea of umbrella sampling is to divide the entire reaction path into several windows. So as long as we have data from distributions that cover the entire CV range, then we can stitch these distributions to get the free energy surface. So how do we stitch a bunch of distributions? There are a few popular methods such as WAN, TI, bar, and M-bar, or even more variations. And M-bar is the method that has provably smallest variance of its result. So it is generally the recommended method. And as we will see later in the exercise, the recommended the protocol of using M-bar can be roughly divided into two steps. And the first step is that we need to decorrelate the time series of the collective variable. So in this equation, G is the statistical inefficiency, and tau is the correlation time. So as an example, a correlation time of 500 steps means that generally it takes every 500 steps to get an uncorrelated sample. And after we get the uncorrelated samples, we can use M-bar to stitch the probability distributions we got from the simulations, and this can be done by reweighting from the mixture distribution as we discussed on Monday. And while these equations might look a little bit daunting, the good thing is that there is a Python implementation that will take care of all these calculations for you. And that is what we are going to learn right now.
Can I pause on this? There's one thing that we haven't covered that much, and that's statistical analysis. A lot of the probability theorems that were derived, like with doing Monte Carlo integrals, doing Monte Carlo sampling to calculate integrals, assume that the samples are uncorrelated. As you know, if we're running a simulation, it takes a long time for it to uncorrelate. Like if there's two minima, it can take a very long time for it to jump from one minima to the next. So one general strategy that you need to use, and if you go back to some of the files from the MDMC workshop this summer, if you want to look back some of the material there, we talk a lot about how to overcome this, making sure we have as much as we can decorrelated samples. So Wei-Tse will show how sort of like it's done. You need to be in general, if you have a very slow system, you need to be a little more careful than this. But for a system like this, where we know what the slow degrees of freedom are, this is a very good way to sort of take into account that noise. So I just wanted to, since we sort of hadn't really talked about that before, I wanted to point out how important that is, that whenever you're doing probabilities, check to see if the formulas you're using are assume that the data is uncorrelated. And if it does assume so, if you want to get good error bars, you need to take the correlation into account. The average, the actual values themselves are fine. Like even if it's uncorrelated data, then your best estimate is to use all the data. But the uncertainties require properly taking care of the correlation. Anyway, I just wanted to call that out. It's important to remember.
Yeah. Okay. I'll answer some questions from the chat. So there's a question asking about if we are using the same TPR file, if does that mean that we are using the same coordinates? And what is that different from running independent simulations opposed to the same simulation being run in different directories? So we ran the simulations in different directory just because that is how running simulations in parallel work. So we must use a multi-dir to run simulations in parallel. So we must use like different directories. But in the first example, you can definitely run each of the simulations separately. There is no need that you can choose to like not run them in parallel. And for the TPR file, so the TPR file will basically encode the topology information, like also like the initial coordinates. But one important thing is that in the MDP file, typically we would generate a new velocity for each different run. So even if the starting configuration is the same, they have like different, they started out with different velocities. So the results will still not be exactly the same, but they should be in like the same ensemble and should be consistent. Okay, I'll probably first start out the notebook, and then I'll answer the question later in the break. Let me see.
So actually, I can handle some of the questions as well if you go to
Sure,
that.
yeah, that would be great. Thank
Okay,
you.
so first, the question of why we need each of our windows to overlap an umbrella sampling. So when you're calculating free energies, you're essentially calculating ratios of probabilities. If you have two umbrellas that don't overlap, you don't actually know how much of each of them there are. You'll have a high uncertainty in that region where there's no overlap. So I don't want to interrupt things too much. This is like a long lecture about what free energy is, but basically, if you want to calculate the free energy surface correctly as a function of some coordinate variable, you need to have some samples at all the values of the collective variables. So you say, Greg, if I want the most accurate free energy value, I should use all the samples. If I want an accurate uncertainty estimation, should I only use uncorrelated samples? That's a great question there. So in theory, you could, if you uncorrelate your samples, you can calculate a free energy value and an uncertainty. What will happen is that even if you only use your uncorrelated samples to calculate the value, the difference between that and using all of them will be within the uncertainty. So fundamentally, whenever you're calculating something from a stochastic simulation, you really your answer is only it's a stochastic quantity, right? It'll have some fluctuations that you do it again. So you could calculate the observable, whatever it is, with all the data or just with the uncorrelated data. Within the noise, those will be the same answers. It won't be the exact same answer because there's some stochastic choice in if you're choosing uncorrelated data, which set of uncorrelated data you use.
Yeah,
I think that's like 90% of the answer. Sure. Okay. Yeah. Excellent. Good.
okay.
I can fill in more later, but let's throw it back to Wei-Tse.
Yeah, I'll continue with the second exercise, which is about running umbrella sampling on bridges 2. So as a quick review, the umbrella sampling can be divided into 2 steps, and here we are going to use the sodium chloride system to calculate the free energy surface as a function of the ion pair distance. So in the first step, we are going to do a pooling simulation, which is also known as DIR-MD. This is just for generating initial configurations for the second step. And in the second step, we are going to fix the configurations with harmonic potentials. So this is the part that we are going to perform in parallel because we are going to like run a bunch of simulations for like a bunch of different configurations and harmonic potential. So yeah, in this exercise, we will run the simulation in the MVT ensemble. This is different from yesterday when we were using MPT ensemble. This is because that the polling code, the umbrella sampling is probably more straightforward in the MVT ensemble, although it is also possible to do it in MPT, but to get started, let's just use MVT ensemble. So just to clarify, but the results that we are going to get in this exercise, although it is in a different ensemble than what we used yesterday, the free energy profile that we get should be qualitatively consistent. Okay, so again, here are a few lines that I use to get rid of the output directory, so you can just execute that. And okay, the first step is the polling simulation. So let's just make a folder for the polling simulation. And then yeah, the purpose of polling simulation is to generate initial configurations. So that divides the whole NaCl into two groups. The first one is the immobile group, which is the atom that we want to fix. And so in this case, we are going to fix the sodium ion, fix the position of the sodium ion using a position restraint, and then we pull the chloride ion away. So the immobile group in this case is the sodium ion. And this can be done by modifying the TOP file, as we will see later. The other group is the pole group, the pro group, which in our case is the chloride ion, because we are pulling it away from the sodium ion. And to enable pulling, we need to specify the pull code options in the MDP file, as we will see later in the exercise. So first of all, the modification of the TOP file. Here is a TOP file that you used like yesterday. There is a little modification, but they are exactly the same. Like in terms of how it works. Basically, I just explicitly specify the molecule type and the atoms for the ions we have in the system. So you can just execute the command. And then to make the topology aware of the position restraint, we need to modify the topology file. And specifically, we are going to add a few lines to the TOP file, which are these lines. So this is a bash command. After execute this command, you should be able to get a TOP file that has these lines as well. So I'll just execute this cell. So what do these lines mean? These added lines basically mean that if the variable post-res NA is defined in the MDP file, then the position restraint defined in the file, this ITP file will be activated. So clearly now we haven't had any ITP file, so we need to create one ITP file right now. So this is a batch command that you can use to create the ITP file. So in this ITP file, specifically for position restraint, we just need to have a position restraint directive, and then in this section, we are going to specify the ion that we are the atom that we want to apply the position restraint. So because the position restraint directive is under the molecule directive, as we saw in the TOP file, the molecule directive we saw only have the sodium ion. That's why we have like the index of 1 here, because like the position restraints directive is not aware of the entire system. And also here are just the force constant along different directions to apply the position restraint. So we can just execute the cell. And then you can also choose to run a GROMACS GRE gen restraint to get a ITP file, but you must be very careful whenever running this command, because as I mentioned, the position restraint would not be aware of the entire system. But if you running this command by passing in the coordinates of the entire system, then the index will be based on the entire system instead of the molecule type of the Na atom. So in this case, it might be easier to just execute this cell to set up the ITP file. So we have just finished modifying the TOP file. Now we want to modify the MDP file as well. So here is the MDP file that you could use in standard MVT simulation. This MDP file is basically the same as the MDP file you used yesterday for your MPT ensemble, except that there is no options specifying the barostat. So we are going to modify this MDP file, and the first step is to make the MDP file aware of the position restraint that we are going to apply. And to do that, we need to define the Postgres NA at the top of the file, as we mentioned earlier when talking about the TOP file. So when specifying this variable, you need like a prefix like -d to define this variable. So yeah, the first line is, so this is a bash command that you can use to generate the MTP file you need for this exercise. The first line is I've already described that. We define the variable, and we basically, yeah, let's first execute this cell. So that's first part of the modification. The second part of the modification is that we need to add the pull code options. So here are the pull code options, and apparently we need to set pull equals to yes to allow the pulling to be performed. And also we only have one collective variable. That's why we are using pull encode equals to 1. And we have two pull groups. One is the NA atom. Well, not the pull groups. The pull group is only the chloride ion in this case. But in this case, we are including like the immobile group when specifying this parameter. So there are two groups, one immobile, one pull group. So we specify this parameter as 2. And the first one, the group 1 is NA, group 2 is CL, and we are applying a distance restraint between these two groups. So we are specifying 1 and 2 for this parameter. And we are using harmonic restraint. Basically, it is the same thing as distance restraint. So we need to specify the type of the type and geometry for the pulling action. And also we allow pulling for any along any direction. So we set it as YYY. If you want to pull the pull group along only the Z direction, then what you are going to specify should be N, and Y. So you just like disable the pulling along the other two directions. And we set this option as yes to allow the harmonic potential to be centered at the initial COM distance between the two ions. And one important thing is the pulling rate, which we set as 0.001 nanometer per second. And we are doing a 250 picosecond simulation. So that will give you like 0.25 nanometer of pulling distance in total. And we are setting the force constant as 1000. And I'm going to talk more about how we can specify, how we should decide the last two parameters. So here are some more explanations. So the pulling rate is basically the rate at which the imaginary spring attached between the ions is elongated. So one thing that we need to consider is the dimension of the box. So the dimension of the box is about like 1.4 times 1.4 times 1.4. So the pull distance must not exceed 0.7 or so, which is half of the dimension, the smallest dimension of the box. So this is to prevent the pull group from interacting with the periodic image of the system. And given that the typical ion pair distance of NaCl is like 0.25, 0.26, a total pull distance of 0.2 nanometers should be safe. So that means that originally we start from 0.26 and we further elongated the distance from by 0.25 nanometer. So after pulling is completed, we will get a configuration where the ion pair distance is around 0.51. But what is important is that when we apply a distance restraint, it doesn't mean that the system will definitely stick at that specific position. There should still be some kind of fluctuations around that CV value. So the upper bound is 0.272. So considering the fluctuations, we need some buffer for that. So 0.5 should be reasonable. So the force constant in this section in the pulling simulation is actually not that important. As long as it is strong enough to pull the pull group away, then you should be fine. So 1000 is typically a reasonable value to use. So right now we are going to run the pulling simulation as we have all the input files ready. So we are going to first generate a TPR file. using the input files. So there's no error. So I'll go on to the next one. So here is the command that we can run the umbrella sampling simulation. So two important flags that we are using here are like the flags for us to specify the paths for the output files, pool.f.xvg and pool.x.xvg. Okay, so now the simulations has been done. And remember, in this polling simulation, we haven't used anything in parallel. So we can just use like one core and one MPI process. There is no parallelization here. So the simulation is done, and you can check that now we have two output files. One is poolf.xvg, the other is poolx.xvg. So these are basically like the polling force and polling distance as a function of time. So at this point, we are going to generate a bunch of initial configurations. As I mentioned, that's the purpose of the polling simulation. So first of all, we need to decide how many windows, how many umbrellas we want to run in the umbrella sampling. Given that we have 32 CPUs available, using 8 windows should be sufficient. So in this very small system, 8 windows is probably enough. But for like larger, more complicated systems, you can use like 20, 40, or even 100 umbrella potentials. So that's basically up to your choice. And here we are going to center. So after we decide the number of umbrella potentials we are going to use, we need to decide the centers for each of the umbrella potential. So here I'm specifying the center of the potentials from the minimum of the ion pair distance, which is around 0.25, to the maximum. Well, 0.6 is not the maximum, but it's around that region. So 0.6 should be reasonable. Also remember that we have an upper bound of 0.7, so we should have some buffer from the upper bound. So we can just execute this command. So you can see that right now, these are the centers of the umbrella potentials that we are going to use, ranging from 0.225, 0.3 up to 0.6. And then the initial configurations, so we are going to extract initial configurations that have an ion pair distance that is very close to these desired centers. So we will do that in the next cell. So basically what I'm doing here is that I have a bunch of timeframes that I want to extract from the ND simulation, the polling simulation, and then we just like iteratively run through all these timeframes. So the first configuration is drawn from 45 picoseconds and so on. So that will give us a bunch of initial configurations for running the second step, the production runs, which I will talk about in the next section. So I think this is probably a good time that we can take a 10-minute break. So
let's pause for questions.
Oh yeah, okay. And after that, we will take a break. Let me see if there is any question from the chat unanswered. If my first simulation is still running, is that normal? So that was 7 minutes ago. So mine only took like 1 or 2 minutes. So if you're still running your simulation, that's probably not normal. Is it still running, Dr. Jankowski?
This is not actually me. I am funneling other questions
Oh,
to the chat.
Yeah, thanks for the clarification. Yeah. Well, hopefully it is finished on yeah. Oh, okay, it's still running. Well, we might want to figure out like the computational resources. Yeah, we can try to figure that out during the break. I'll take a closer look at that.
So one thing on the performance plots, especially with small systems, it can be a little weird.
Yeah, for small systems, things could be a little weird, and especially we are using like a shorter cutoff, and the domain decomposition could be different.
But one thing I'd always say, if if the simulation is running much slower than you think it should, then one thing you might want to check is this is because this comes up all the time, is looking at the GROMACS outputs or whatever the MD simulation code you're looking at, and try to figure out how many cores it thinks it's using. Sometimes there's a typo somewhere and it's trying to use way more resources than you think it is, and it's like just getting confused with itself.
Yeah.
So you do have to check the times. Also, it's sometimes repeating a test quick. With all these timing things, always you should run relatively short. So
Yeah. And also sometimes GROMACS have some kind of error that it would not explicitly complain. It will just like hang in there for some very few cases. So it's always a good practice to check the output files if you think your simulation are running much longer than you expected.
yeah. Basically, we can't tell you exactly why because there's so many things that could go wrong. So pointing you where to look at, look at the output files, try to repeat it to try to bring out more information. Woodrow's asking, can you elaborate on how you pick the value for the force constant?
So for the pooling simulation, we are not fixing any configurations. So we don't need to worry about anything about overlap between distributions. The force constants for the pooling simulation is only for pulling the chloride ion away. So as long as it is strong enough to be able to generate a bunch of configurations, that should be fine. So the force constant in the pooling simulation is not that there are not many restrictions. What's important is the force constant in the second step where we fix the configuration. So as we will see later, we will be more careful when setting the force constants for the production runs. Yeah, hopefully that answered your questions. Okay, if there is no further question, let's take a 10-minute break. Let's try to come back at 2:09. Okay. Yep. I'll stop sharing here, I guess. And if you have like any further questions, feel free to ask in the chat and I'll try to answer that during the break. What's the difference in the system thermodynamics between a pooling simulation and meta dynamics on the geometric mean? Okay.
Geometric mean of what?
So instead of pulling two things apart, whatever they are, what, like if you did a well-tempered meta dynamic simulation on those two, whatever you're pulling, and the collective variable was the geometric mean.
The geometric mean of the
But other distances between, like the same, just instead of pulling, like in this case, your sodium and chloride apart, you did metadynamics on the distance between sodium and chloride with the same maximum distance as the grid.
Do you mean like calculating the geometric mean of the distance on the fly while running metadynamics, or do you mean like another specific variable? Because like so I guess I'll like try to first address the difference between metadynamics and umbrella sampling. So well, there are some things in common. When we are performing a pooling simulation where like one part of the system is pulled away from the other part, that is basically like not an equilibrium process because we are constantly applying forces. And in metadynamics, we are constantly applying like biasing potentials. And in Plummet, what is done is that it will calculate the derivative of the potential, the biasing potential, which will turns into some kind of effective force due to the biasing potential. So that means that when you are running metadynamics and you are like adding up potentials, that is also like a non-equilibrium process. So that's like something they share in common, but I'm not sure if I understand the CV that you mentioned, like the geometric mean.
Yeah. But generally, like in metadynamics, what you have this collective variable, and then you put in, you like add a hill wherever you are, and that hill pushes you off.
Mhm.
With this non-equilibrium pulling simulation, what you're doing is you have like an AFM tip with like a spring attached to it, and you're dragging that tip along, and you're pulling along the ion to follow it.
Yeah.
Mhm.
Also in umbrella sampling, typically it is required. Well, it is at least common to apply a position restraint to at least a part of the system to make it immobile, and while you are doing your pulling, so that would make the pulling easier. If you don't have like position restraint for the immobile part, for the part that should have been immobile, then basically the whole molecule that you are pulling will just like drift in your water box, and the pulling will not be as effective as the case you are using a position restraint.
Okay.
Yeah. Is anyone still have simulations like running, and like if you're not able to finish the simulation in a reasonable amount of time, let me know and maybe we can take a look at that. This pulling example with a harmonic potential between a pair of ions makes sense when the CV is the ion pair distance. How will we implement a similar process with a more complicated collective variable of like radius or gyration in the polymer? That is a great question. I haven't really done umbrella sampling using like some other forms of restraint collective variables, but what I know is that it is still possible that you like apply, like for example a dihedral restraint, or some restraint for some other internal coordinates. The point is that in GROMACS it is harder to define such a restraint. It is possible to do it in like dihedral restraint, but for some more complicated CV collective variable, it is harder to use that in GROMACS. But in Plumet, it is also possible to run umbrella sampling in Plumet, where you have a much higher flexibility to define your customized restraint. So in your case, if you want to do like a radius of gyration, then you can also define it in using the Plumet code to define your restraint during your sampling simulations.
Yeah, Plume does a lot of really fancy collective variables, and
Yeah.
the plugins that Omar was showing yesterday can also be done, can be used to just say, don't do any fancy metadynamics, just do a simple biasing potential on this fancy collective variable I came up with.
That is,
And I think Wei-Tse, one of you, I don't know if we'll get to that examples, but you have an example on that.
yeah, I have it ready.
in 5. Yeah, you can see. We might not have time.
I think we are on track though, so
Yeah.
hopefully we
If-
can get to that.
But if you have a CV, like, the $1 million question is, what CV should I use? But that's really a science question. It's what are the slow degrees of freedom of this system, which is like really the science question.
Yeah.
What we're hoping is that after this, you'll be in a much better position that you could answer that question in your research. We can't tell you the answer, but we want you to be able to answer it.
And the entire field of free energy calculations is probably like $1 billion question. People have been doing that for several decades.
If you could figure out a general way to find the slow degrees of freedom in complex in proteins where the ligand binding like induces a conformational change, then yeah, that might open up a lot of drug discovery that's not possible now.
Yeah.
And I apologize for people who do more catalytic materials or polymer materials that I keep giving biology examples. That's what I spend a lot of time thinking about. So multiple time scale is true everywhere though. This is all molecular systems. So
Yeah. Okay, it's 2:09 right now, so I'll probably continue with our next section of the workshop.
and so I would recommend people like stop if you did do an RM if you did do an RM small, you should quit that and restart with RM shared.
Yeah,
Correct.
right. Okay, so welcome back to the second part of the umbrella sampling tutorial. So as a reminder, in the first part, what we did is that we modified the topology file, the MDB file, and we perform a polling simulation from which we can generate a bunch of initial configurations for the second step, which is what we are doing right now, the production runs. So like at this point, the GRO file and TOP files are basically ready. The GRO files were generated from the polling simulation. For the topology file, we could just use the topology file we used in the polling simulation. So really, the only difference is that we need to modify the MTB file specifically for this step again. So I have listed 3 changes that we need to make, which I'll execute in the batch comments later. But the 3 changes are the simulation length. So we were doing like 200 picoseconds for the polling simulation, but this time we are going to do like 500 picoseconds. And remember, we have like 8 umbrella windows. So we are going to run like 500 picoseconds for each of these 8 windows. And the polling rate should be set at 0. That is because that in the second part of the umbrella sampling protocol, we want to fix the configuration at a certain CV value. So there is no need, and you shouldn't change like the ion pair distance like deliberately by setting a polling rate. So the polling rate should really be at 0. And also here we are choosing the force constants, and we are going to set it as 8,000, which sounds pretty large, but we are going to see it's actually pretty reasonable. So we are going to use 8,000 instead of 1,000. So here are just a bunch of comments that will help you to accomplish all these steps to give you the MDB file that you can use directly in this session. So the first line here, we are just basically first copying the MDB file we used for the polling simulation, and we are going to modify the file. So these are the 3 parameters we are changing, and using the seed commands to do that, to replace the values. And then you can execute this cell to take a look at the MDP file after modification for this part. So now we have the grow file, we have the TOP file, and we have the MDP file. So we are able to generate a TPR file for each of the 8 simulations. So that can be done in a for loop. Here I'm using a for loop where the value of I runs from 0 to 7. So here I'm using a $sign to use it as a variable. So you will basically copy the grow file, TOP file, and MPP file from the input folders to each of the folders you have right now, like sim 0, sim 1, sim 2, up to sim 7. And then for each of these, each of these folders, we are going to run the grump command to generate a TPR file. There it is. This command is nothing different from the grump command that we were using previously. And oh, well, actually, so the grump command that we were using in the previous step, there was an additional, well, so both of them are the same, just to clarify, but they are probably different from the grump command that you would use for standard MB simulation where there is no position restraint. The only difference is that right now we are using the additional -r flag to specify the coordinates for the position restraint, and we have position restraints for both phases of the umbrella sampling. So we still need that flag. So here gives you 8 TPR files for 8 simulations, and there's no error, so we are good to go. So right now we have 8 TPR files. That means that we are ready to run the 8 simulations in parallel. And importantly, you can choose to run all these simulations separately because they are not coupled. They are totally independent from each other, just as we've seen in the first exercise. You can definitely choose to run them separately, but here, just as an example, we are running them in parallel. And also, if you have like 100 umbrella sampling simulations, you probably would prefer to run them in parallel instead of like in a serial manner. So the command is nothing different from what we used previously. Basically, the point is that we are using the multi-dir option to specify the folders that we have the simulation inputs. So here is an alternative way that you can specify the value for multi-dir. In the previous example, we explicitly wrote out like sim 0, sim 1, sim 2, and sim 3. Here we are just using sim underscore, and in the curly bracket, then we can define the range where the index is going to run. Okay, so I should have run this like 1 minute ago, but well, this simulation should take about like 30 seconds. The system is very small, so it shouldn't take more than 1 minute. So let's just wait for a bit. Okay, so now the simulation has done. It's okay. It only took like 16 seconds, so that was really fast. So same as the polling simulation, as you can check now, we have the poll.x.xvg file and the poll.f.xvg file. So one important thing to check after you run your simulation is to check the overlap between the neighboring distributions for your collective variable. So poll.x.xvg file contains the data of your ion pair distance as a function of time. So that is where we can plot where we can use the data and plot the distribution. So here are just a bunch of settings for plotting that I like, and then here you can plot the distribution. So here I'm just like using mp.logtext to reading the grump.xvg file and process, and then for each of the 8 poll.x.xvg files from different simulations, we can plot a histogram for the distribution. And here you can see that we basically have overlap in every pairs of neighboring distributions, which is a good thing. So that is a good sign that 8,000. Oh, there is a. Let me see. Okay, I'm not sure what happened here. There is some kind of overlap. I'm not able to read that, but basically the point is that the 8,000 should be the reasonable value to use here. So it does require some kind of experience to when you are deciding what force constant to use. But basically, this is an example that could like give you some experience, right? So the force constant in the production runs where we want to fix the configurations, as I mentioned, is very important. So if the force constant were too large, the spread of each distribution will be too narrow. So there's a risk of not having any overlap between some neighboring replicas, neighboring distributions. So also the force constant shouldn't be too small. If the force constant is too small, then the system will have the tendencies to drift back to the nearest metastable state. So you will like drift away from the desired center you want to fix your configurations. So that is kind of considerations that you need to be aware of. So now here comes the first open-ended questions that I put in the exercise. How can we further improve the overlap? Oh, there's a typo here. Further improve the overlap between neighboring distributions. So I'll give everyone like 1 minute to think about this question. And here is a figure that we are going to focus on. So the goal is to further improve the overlap between these distributions such that because you can see that right now there is like an uneven overlap. For these distributions, we have pretty even overlap, where for the first two distribution, it seems that there is a pretty large amount of overlap, and it's probably better if we can shift the distribution in this direction a little bit. And in fact, the second distribution was centered at 0.3, but you see that, well, we wanted to center it at 0.3, but you can see that now the center is not exactly at 0.3. That is because that this distribution is very close to the metastable states at 0.25. So it has a pretty strong tendency to drift back to this specific metastable states. So that means that 8,000 as the force constant for this specific distribution is actually not strong enough to fix the position of this configuration at 0.3. Okay, so I guess 1 minute has probably passed. So let me see if there's any answer in the chat. Okay, well, there are some questions, but I'll probably answer that later. But yeah, so maybe for the next question, people could, if you want to discuss, you can put your answers to the chat so that I can see how people think. Increase the force constant in that region. That is correct. More windows. Okay, yeah, these are the two answers that I was expecting. So first of all, we can consider increasing the force constant here such that there is no drift from 0.3. That is the first workaround. The second workaround is that for this specific region, we can probably put 1 or 2 more windows to like ensure much more overlap. So that those answers were perfect answers, and thanks a lot for participating in the Q&A session. Yeah, so for so this ends the second section where we have finished the umbrella sampling simulations. So after we finish the umbrella sampling simulations, we can run free energy calculations of using the simulation outputs. So specifically, we are going to use M bar here. And the goal is to get a free energy surface consistent with the one that you got yesterday from your metadynamics tutorial. So here is a big block of code. I try to make the code like shorter, but this is probably like the size that I could get while still maintaining like readability. So I won't go into details about every line of this code, but I will try to summarize what this code is doing. So first of all, we need to set a bunch of parameters in this code, like the number of replicas and the temperature and the corresponding conversion factor for converting KT to kilojoule per mole. And also we need to have like the number of data points for each simulation, you can get it from easily from your pull x.xvg file. And this is basically the range we want to plot the free energy surface. We can just like set it as 0.25 as the minimum and 0.65 as the maximum. And we are using 8,000 as the force constant. So just to clarify, in umbrella sampling simulation, you don't need to have exactly the same force constant for all the windows. You can have like different force constants for different windows. So in that case, you can instead of using numpy.1 times 8,000, you can specify an array of force constant that you are using in your simulations. Okay, so that is the first section, specifying the parameters. Then, as I mentioned, the protocol that we recommend when using nbar is that we first want to decorrelate the time series of the collective variables. So basically, this section is using some functionality like time series statistical inefficiency to decorrelate the samples. So we will get a bunch of uncorrelated samples at the end of this section. And after that, we can feed the uncorrelated samples to the nbar estimator to get the free energy surface. So this part, we will calculate the free energy surface. We will output it to a fes.dat file, and then we will plot the free energy surface. So that's basically what this code is doing. So we can execute that. Will take a few seconds. Okay, so this is the free energy surface that we got from the simulations, and it looks pretty much the same as the one we got yesterday from the meta dynamics tutorial. If you remember that the free energy barrier was around like 5, it was a little bit higher than 5 kT. So this is like qualitatively consistent. I mean, visually consistent, but we will take a closer look when we compare umbrella sampling with multiple Walker's meta dynamics later. So here comes the second open-ended question. So from this plot, you can see that for some regions, the uncertainty is smaller. And why is that? I'll give everyone 1 minute to think about this question. And if you have any ideas, you can put it in the chat, and we can discuss that later. Okay, there is a question from the chat, like, is it okay if we still use 1,000? For the second step, 1,000 would be too small. As you see, like using 8,000, even if we were using 8,000, there was at least one distribution that drifted away from the center we wanted it to be. So 1,000 is definitely too small for this specific case. Yeah. How do you pick the appropriate force constant? Does it depend strongly on the system? Well, yeah, it's system dependent, but it also involves some kind of trial and error. And I would say like several thousand is probably a generally good starting point. So in this case, like we are trying to like break the ionic bond. So you could have like an idea of several thousand should be a good starting point. Okay, let me see if there is any question. There are any answers. More overlap between the distributions causes less uncertainty. Yes, more samples in that region. Yeah, yes. Yeah, okay, all these answers are correct. So basically, a lot of people are saying that the uncertainty was lower for some region because that there were more samples for that region. And to check that, we can plot the histogram for the of the uncorrelated samples from each distribution. So you can see that the statistical inefficiency or the correlation time for different distributions were actually different. We can see it here, like different distribution definitely have like different statistical inefficiency. So here you can see that for some of the distributions, we have a lot of samples. So you can see that in this region, the uncertainty was pretty small. So that those answers were correct. Yeah, and thanks again for engaging in the discussion. So here are a few references that I want to mention, like this is a paper that proposed M-bar, and like another paper that explained M-bar from another
Oops.
angle. And
First
also,
one, first one's incorrect. First one's not the original one, but
oh yeah, I accidentally, oh yeah, pasted the wrong one. I'll correct that later after the workshop. And also I put a review about umbrella sampling that was like 10 years ago, but it was a good review. It didn't like mention the use of M-bar. It was basically using WAM. I know a lot of people use WAM for umbrella sampling, but really like M-bar is like the method that has like provably smallest variance. So we would recommend using M-bar. So that ends our second tutorial on umbrella sampling. Oh, and these are a few takeaways that we've covered. Like umbrella sampling is composed of two steps: polling, simulation, and production runs. And the force constant for polling the simulation is not really important. There are not many restrictions, but it is important in the production runs. And also we are able to use M-bar to get the fringe surface. So these are the takeaways. So are there any questions at this point? If not, then I'll continue with the next advanced sampling method. Let me